We often operate under the assumption that physics is a solved game. We look at the cosmos and see trillions of stars following a single, unified set of universal rules. In reality, our understanding of the universe is fractured. The laws of physics are currently split into two frameworks that cannot occupy the same space. General relativity defines the macro universe. It treats gravity not as a force, but as the literal curvature of the fabric of spacetime, accurately predicting the behavior of planets and black holes. Meanwhile, quantum field theory governs the micro-universe. It successfully describes the chaotic interactions of subatomic particles through discrete packets of energy. Problems arise when we combine them. Because relativity requires space to be smooth, and quantum mechanics describes it as jittery and discrete, the mathematical clash produces infinite values and nonsensical results. Since the universe exists as one seamless reality from atoms to galaxies, our current reliance on a three-dimensional framework is proving to be mathematically insufficient. The most visible evidence of this breakdown is the staggering, unexplained weakness of gravity. The static electricity on a pen lifts a paperclip, overcoming the gravitational pull of our 5 sextillion-ton planet. Compared to electromagnetism, gravity is weaker by a factor of 10 to the 40th power. Mathematically, a massive portion of gravity's strength is simply unaccounted for. During the Big Bang, physicists believe all forces were unified as a single superforce. Gravity's current state represents a mechanical departure from that symmetry. To reconcile the macro and micro worlds, we have to determine exactly why gravity appears so uniquely diluted in our three-dimensional experience. String theory emerged as a potential bridge. It suggests that if we look deep enough, the friction between relativity and quantum mechanics disappears. This theory replaces zero-dimensional point particles with one-dimensional, vibrating strings of energy, roughly 100 billion times smaller than a proton. Much like the strings on a violin, these filaments create different notes based on their vibration. One frequency manifests as an electron, another manifests as a photon. However, calculating these quantum vibrations creates a problem. In our standard model of space, equations yield impossible values, making the strings physically unstable. This occurs because restricting the math to 3 dimensions means the strings lack the room to properly vibrate and resolve their energy. The math only stabilizes when the equations are allowed to expand. String theory requires a larger arena than the volume we can perceive. Michio Kaku compares this struggle to a shattered vase. If a crystal vase is smashed on a table, the shards are easy to reassemble if you can move them in 3 dimensions. But to a 2-dimensional being living on the surface of the table, the shards would appear as disconnected flat lines. Without the dimension of up, these beings could never see how the pieces are supposed to fit together. We are in a similar position. We are attempting to unite the fragments of our physics while lacking access to the higher dimensions that make the union possible. The math requires 10 dimensions to function, and an 11th dimension in M-theory to account for membranes that could hold entire universes. We cannot perceive these dimensions because of a process called compactification, which suggests they are tightly curled at a scale beyond our reach. Consider an ant on a garden hose. From a distance, the hose looks like a one-dimensional line, but to the ant, the hose has a second dimension, a circular path that wraps around the tube. These extra dimensions exist at every point in space, but they are compacted so small that only subatomic strings are small enough to experience them. These hidden dimensions provide a physical explanation for the missing strength of gravity. Recall that general relativity defines gravity as the curvature of space-time itself. While other forces travel through space as fields, gravity is the geometry of the arena. Because gravity is tied to that geometry, it interacts with every dimension available. Its power is siphoned into the curled-up dimensions, diluting the influence we feel in our 3-dimensional slice. This multi-dimensional folding does more than just weaken a single force. The specific geometric shape of these extra dimensions, how they are twisted and knotted, restricts how a string can vibrate. Because the vibration determines the particle's mass and charge, the geometry of the hidden dimensions acts as a cosmic DNA. The shape of the folds dictates the fundamental constants of our specific universe. This framework is now moving toward experimental verification. At the Large Hadron Collider, physicists search for evidence of gravity leaking out of our dimensions. They look for particles that seem to disappear during collisions, potentially siphoned into the higher dimensional scaffolding. String theory suggests that the universe is governed by an invisible, multidimensional architecture that defines the very limits of reality.